All right, so we have seen how the basic tenets of quantum mechanics go in the evening session yesterday. Today I will start with, given a classical system, how do you go about quantizing it? Well, that's what is going to be done for the quantum field theory in flat space. So idea is, given a classical system, how do we quantize it? So this process is called the canonical quantization method, and I'll illustrate it using the simple harmonic oscillator. But before that, what do we mean by saying that we are given a classical system? Basically, it is the Lagrangian which is the most fundamental stuff in classical dynamics, and Lagrangian, we know, is a function of the position, meaning generalized position, which normally you use q. I'll use x and x dot, and in general it can have explicit dependence on time, but we are talking about conservative system where energy is conserved, so we will not include an explicit dependence on time. So a classical system, I will illustrate using only one degree of freedom. So x is the single degree of freedom and x dot is the generalized velocity. So first step in going about quantizing is go into the Hamiltonian formalism. In Hamiltonian formalism, what happens is you don't use configuration coordinate x and velocity x dot, but you go to x and p, momentum. And how do you do it? First you find out what is the momentum. By definition, momentum is del L by del x dot. And from this equation, you can invert this equation and get x dot in terms of p. Once you have got it, then Hamiltonian, which by definition is a function of position and momentum, is defined to be x dot p minus L. P is already defined, and by inverting the equation you can get x dot in terms of p. L to begin with was a function of x and x dot. X dot you will again rewrite in terms of momentum, so you will get a function of position and momentum which is called the Hamiltonian, classical Hamiltonian, whose interpretation is it's the energy as a function of position and momentum. Then in classical dynamical system, what is very important is the canonical, or rather the Poisson bracket of position and momentum for a one-dimensional system is 1. This is all about classical dynamical system. Now we want to quantize it. Quantization is, so the process of quantization is position now becomes an operator. It goes to a Hermitian operator x cap. Momentum goes to the momentum operator p, and Hamiltonian goes to the Hamiltonian operator. But how have you turned them into an operator? They are operators such that the Poisson bracket will now become commutator, and so Poisson bracket xp will become the commutator xp. And the Poisson bracket of xp is 1, means the commutator bracket must be I into h bar. So when you do that, your classical system has taken the form of a quantum system. This is the standard method. I will illustrate first using the case of harmonic oscillator, simple harmonic oscillator. These are all well known. I am just doing it so that I can straight away go to quantum field theory. So we know that for a simple harmonic oscillator, your kinetic energy is half mx dot square, potential energy is minus half m omega square x square. So this immediately tells me, using this formalism, this is your, L. This immediately tells me that P, which is del L by del x dot, from this term, you can see it is nothing but mx dot, which implies x dot is P by m, and therefore the Hamiltonian x dot P minus L, x dot is already P by m, so P square by m, minus L, half mx dot square, half m x dot square is P square by m square, plus half m omega square x square. It becomes therefore P square by 2m by plus okay. This is the classical Hamiltonian. Now we want to, this is classical SHO. Now we want to go to quantum SHO. So quantum SHO, now your position is an operator, momentum is an operator, Hamiltonian is an operator, which is P and X are operator such that the position and momentum operator, they satisfy the canonical commutation relation, namely X P is IH bar. Okay. So this is your quantum simple harmonic oscillator problem, and in quantum mechanics, what do we want to know? What do we want to do? We want to get the exact energy eigenvalues, exact energy eigenstate. Once for any quantum system you know the exact energy eigenvalues and exact energy eigenstate, the problem is solved. Why? Because any state, its time evolution, since it's given by e raised to power minus I by h bar Hamiltonian operator acting on psi of t naught, psi of t naught can be expanded in terms of energy eigenstates, and this acting on energy eigenstate, we know the eigenvalue. So the full evolution, if you know all the energy eigenstates and energy eigenvalues, then I know that if psi of t naught is given by Ci independent of time ket Ei, then applying this on this, we get psi of t. Entire time evolution is determined. This will be just by applying this operator on this state. This becomes Ci. Ci is anyway well known from earlier case, minus by I by h bar E of t minus t by t naught Ei. So the entire dynamical evolution is known. Ket Ei is known, Ei eigenvalues are known, Ci's are known, full time evolution is known. So purpose of all quantum theory is to get the exact energy eigenvalues, exact energy eigenstate. Whole dynamical problem is solved. Okay, that's why energy eigenstates and energy eigenvalues become very cardinal in quantum theory. So when you do simple harmonic oscillator, that is what is to be done, and Dirac developed a beautiful approach where you don't have to use differential equation. Purely through algebra, you can solve the energy eigenstates and energy eigenvalues. And the idea is to define two operators, raising and lowering operators, A and A dagger, by so essentially you introduce two operators A and A dagger and rewrite the position operator as and momentum operator as okay. So introduce two operators. A is not self-adjoint. A is not equal to A dagger. But X and P are self-adjoint, meaning Hermitian. You can verify. You can verify this is indeed Hermitian. And then what you also demand is that X P commutator must be equal to I H bar. From this, you can immediately prove, by substituting this here, you will find that A and A dagger are such that A dagger commutator is the identity operator. Just substitute this here, you will find that A and A dagger must satisfy the commutator A dagger. Now, I will not go through Dirac's argument. You can show it comes from, before that I must write down. So, if you now use this X and P in terms of A dagger, you can get the Hamiltonian. You can find that the Hamiltonian operator can be simply written as H bar omega times A dagger plus A dagger A. Okay. I'm not going through the algebra. The algebra is very straightforward and you have all done it. I'm just reminding you what happens. And from this you can immediately find out, and there is something more. You can define an operator n which is A dagger A, which will later on turn out to be the its eigenvalues are integers. You can prove it. Its eigenvalues are integers. So it will give you the level of the energy eigenvalue. So H can also be expressed in terms of A dagger A. Why? Because A dagger commutator is 1, meaning A dagger minus A dagger A is 1. So A dagger, so this whole thing can be written as, probably there is a half factor. I think there is a half factor. The whole thing can be therefore written as H bar omega A dagger A plus half. Okay. Because A dagger is 1 plus A dagger A. So 1 plus A dagger, so there will be 2 and the half factor will, and you will get this. And Dirac's insight was to see that from the fact that the Hamiltonian operator is this, and the fact that the expectation value of A dagger A is always positive, obvious. He deduced that there is a lower bound to the energy, and from that he realized the minimum energy is such that A acting on the lowest energy state, let's call it E0, is the zero vector. That was, I don't want to go through the argument. It's a great argument. No differential equation is involved, just from the fact that A dagger A it's from the eigenvalue of A dagger A is always, n equal to 0, 1, 2, you can deduce that there will be always the minimum state which is annihilated by the operator A. And then you can show that the next energy eigenvalue E1 is proportional to A dagger acting on E0. Then thereafter E2 is proportional to A dagger squared, that means A dagger acting on E0, and so on. So that the eigenvalues of A dagger A are numbers, and you get the energy eigenvalues. En, ket En is simply half h bar omega, or h bar omega n plus half, not ket En, the eigenvalue En. And ket En is proportional to A dagger to the power n acting on the lowest energy state corresponding n equals 0. This can be very trivially derived. I am only giving the results. This is something I assume has been done in all quantum mechanics course. The important point to notice is the minimum energy for the harmonic oscillator is not 0. Minimum energy is when n equals 0, it is half h bar omega. And this is the 0 point energy of the oscillator. That means the lowest energy of the harmonic oscillator is not 0, it's half h bar omega. We'll see a similar thing happens in quantum field theory, and it is very important. It is related to the cosmological constant. Okay? Yeah.
Can you just clarify one thing for my own understanding? That when we operate this creation and annihilation operator, so that is basically a number of particles, right? And the state is
At the moment, not number of particles. At the moment, for a simple harmonic oscillator, A and A dagger, A is a lowering operator, means every time it operates on a energy eigenstate, it reduces the energy eigenstate to a energy eigenstate of a lower energy value. Because why? Because if you can find out the commutator of H with A, the reason why it happens is commutator of H with A will turn out to be minus A, while commutator of H with A dagger is positive A dagger. So therefore what from here I will show, so supposing H acting on ket E is an eigenstate of H with eigenvalue E, supposing this is true. I will now prove using this commutator that H acting on A on E will lower the energy. How? Let's go through it. H acting on A acting on ket E, but HA minus AH is minus A. So HA is nothing but how much? HA minus AH is minus A. So it is AH minus A, which is equal to AH acting on E minus A acting on E. But this is nothing but H acting on E is eigenvalue E. So this is E, A, E minus A, E. So there is nothing but E minus 1, A acting on E. This minus, actually I should have mentioned this should have been H bar omega, not minus, H bar omega into H bar omega. So there will be H bar omega. In other words, if ket E is an eigenstate of the energy operator with eigenvalue E, A acting on E lowers the energy by H bar omega, because H acting on AE is E minus H bar omega A into E. A dagger would have done the reverse. A dagger acting on E is also an eigenstate with eigenvalue E plus h bar omega. So A dagger raises the energy while A decreases the energy. In harmonic oscillator, there is only one particle. But now we will see that when you do a real scalar field, it's a field. The field can be treated as a collection of harmonic oscillator. That is the magic that takes place. Okay. Are there any questions? I have just given you a short introduction to harmonic oscillator that you have already studied. But if there is any question, you must stop me and ask me here itself. Well, we are going to apply all these when we do the quantization of the scalar field. Is there any notion that needs to be discussed at this point?
There was a question on Zoom. One of it was, what is the physical significance of the Poisson bracket of X and P?
Physical significance. Well, the Hamiltonian formulation or Lagrangian formulation on classical dynamical system is a formalism which gives an algebraic interpretation of the Newtonian dynamics. So, Poisson bracket, as the definition of a Poisson bracket, is any dynamical variable A, comma B, which are function of Q's and P's or X and P's, by definition is del A by del X, del B by del P, minus del A by del P, del B P by del B by del X. This is the definition of Poisson bracket. And Poisson bracket is a mathematical quantity which is antisymmetric, linear in two arguments, and satisfies the Jacobi identity. So it has a Lie group structure, it has a Lie algebra structure. So you can formulate the classical dynamical equation in terms of Lie algebra and Lie groups. Is very well developed in a book written by Mukunda and Sudarshan on what is that book's name? Some perspectives of classical dynamical system from group theory perspective. So it is a mathematical structure. There is as such no physical interpretation of the Poisson bracket. Earlier people would have thought that, oh, these are all mathematics. Why should we learn if I can do a problem using Newton's force equation? Why should I learn this mathematical formulation of classical dynamics? But lo and behold, the surprise was when quantum theory was being developed, Dirac immediately realized that there is a correspondence with the classical Hamiltonian formulation with quantum mechanics. If you know about Dirac's reminiscences, Dirac, when he saw Heisenberg's matrix mechanics, he suddenly realized that there is something he had encountered before. And he realized that the Poisson bracket, when it becomes commutator bracket, it is exactly like the commutation of two matrices. So in other words, Poisson bracket by itself doesn't have any physical significance. But when we make a transition from Poisson bracket to the commutator bracket, then we suddenly realize what the physical significance is. Because commutator bracket, when of two observables, if the commutator bracket is non-zero, means it leads to uncertainty principle in X and P. By now you all know that if two observables don't commute, you can't have simultaneous eigenstates. That means you can't simultaneously measure two observables which do not commute each other. So the physical significance of commutator bracket is there, that two objects whose commutator bracket is non-zero must satisfy an uncertainty principle, but not for the Poisson bracket. I don't have any physical except the Liouville's theorem. I mean, Poisson bracket, there is some theorem called Liouville's theorem which says that if you have a distribution in position and momentum, then the distribution del d by dt of that distribution is del by del t of that distribution plus Poisson bracket with the Hamiltonian, which tells you how the phase space volume evolves with time, and that is given in terms of the Poisson bracket. I hope I have satisfied the person who has raised this question.
There's also a question about how zero-point energy is related to cosmology.
Yeah, that I will come to. So, first of all, let me reiterate that the non-relativistic simple harmonic oscillator, when you quantize it, the lowest energy, that is ground state energy, is not zero. It is half h bar omega. So someone will say, doesn't it contradict the fact that in classical mechanics, my oscillator, either you can take a bob oscillating because of a spring or a simple pendulum hanging because of a bob in uniform gravity. The bob in classical dynamics, we know the lowest energy configuration is when the bob is not oscillating, and it is at the lowest potential energy. Total energy is zero. But this is only classical dynamics. We know quantum mechanics prohibits anything to have exact position and exact momentum. So therefore there should be an uncertainty. The uncertainty principle itself says that you cannot have absolute zero energy, because zero energy corresponds to the position being definite, momentum being zero. It is not allowed by uncertainty principle, and hence the ground state cannot have zero energy. So 0-point energy in a sense has to be there to be consistent with uncertainty principle. Right. So now I will make a transition to the field theory. Namely, I will of course illustrate taking only the real scalar field. So, since there was a question about Poisson equation, we also will encounter in general relativity killing vectors. So people might think physics is very violent. We talk about Poisson, killing, etc.
So can E act on zero against it?
What?
E
Zero meaning lowest energy state, which in some book the lowest energy eigenstate E0 is written as ket 0, and by definition the lowering operator cannot go beyond the energy. Energy is bounded. So A acting on the lowest energy eigenstate annihilates it, means A acting on 0 or lowest energy state is identical to 0 vector. That's the beautiful insight that Dirac has. So remember the whole canonical quantization method. We'll use the same method when we quantize the classical, real classical scalar field. Anyone wants to get deep inside into canonical formulation of classical dynamics should read that book written by Mukunda and Sudarshan called Prospects of Classical Dynamics or Perspectives of Classical Dynamics.
Classical dynamics, a modern perspective.
What?
Classical dynamics, a modern perspective.
Modern Perspective, yeah, that is the name of the book. You know, I mean, people like Mukunda, I mean, they have such deep mathematical insights in physics. That breed of physicists are slowly disappearing. Yeah.
There's another question. Even in classical physics, the zero of the potential energy is arbitrary. the reference value can be taken to be any constant.
Correct.
So does it mean that in quantum mechanics the reference value of energy is no longer arbitrary because you have a 0 point energy?
A very good question. So the question says that, look, in classical mechanics, I can add any constant to the potential and absolutely we don't have any physical impact of the zero. So what happens in quantum mechanics? That's a good question. The answer is this. It just adds to a constant phase. So let's take the usual Schrodinger equation. We have already seen the solution, right? So H in general, if I take H naught, and H naught has a potential function, but I add an arbitrary constant. So V is an arbitrary constant. Okay? So the question that is telling me is that if I take an arbitrary constant V, call it V naught so that it is the constant. Does it affect the quantum evolution? Let's see. After all, we know how the evolution is from yesterday's evolution equation. This is nothing but minus I h bar h. Earlier I had not added the constant, so h naught t acting on psi 0. No, it is a constant, pure constant. So the question is about adding a pure constant, just like we added a pure constant in classical dynamics. So when we didn't add the constant, the evolution of the quantum system is given by this equation. Now, suppose someone had added the constant and his Hamiltonian of the h naught plus, so his evolution will be psi prime of t is e raised to power minus I by h bar h naught operator plus a constant t psi naught. In other words, you will get the result that there will be a constant phase multiplied by time multiplied by your old psi of t. So the person who took the Hamiltonian to be h naught plus v, that means he added a constant, his wave function, his state will be different from the person's state who did not add the constant by this e raised to minus I by h bar constant into t. Okay, but physics will not change because any thing will depend upon inner product, any probability will depend upon the inner product of this with another state, and the constant phase will not matter in the probability, it will not matter in the eigenvalues, nothing. Only the state vector will have a fluctuation because V0 is a constant, it will be just fluctuating. But
still there is a notion of absolute value of the lowest energy a quantum oscillator can have.
no, the eigenvalues will not change because eigenvalues will be just added by a constant. Eigenvalues will be added by a pure constant, that's all. Just like classical mechanics, the total energy will be added to a constant, but probabilities, etc., will be invariant because mod square will come in and this phase e raised to power minus I by h bar v naught t, in the mod square they will not appear. It is a constant, there is no dependence on position or anything. Right, now the real scalar field. So, the simplest Lagrangian density, okay, there are certain things we must, before I go into the mathematics. In standard quantum mechanics, my degrees of freedom is countable. Like for example, in the harmonic oscillator, There was only one degree of freedom, x. Okay. If you take hydrogen atom, in hydrogen atom, if you don't include the spin of the electron, there are only 3 degrees of freedom, the x, y, z coordinate of the electron. But now, the moment we talk about fields, fields are a function over 3-dimensional space and time. That means at any given space, time, there is a value of the real scalar field. At any another value. So you have infinite degrees of freedom. And we need to quantize such infinite degree of freedom system. In the previous case, we talked about Lagrangian, but here when we talk about fields, it is more suitable to talk about Lagrangian density, Hamiltonian density, because it's a thing which is depending on the continuum, space-time continuum. So density will be what is known to you. Of course, you can integrate over space. If you integrate the Lagrangian density over space, you can get your Lagrangian. So the Lagrangian in field theory will be integral over the space of something called the Lagrangian density, and the Lagrangian density for the scalar field will be, of course, phi and phi dot. And of course, if energy is to be conserved, it should not have explicit dependence on time, but we can put the explicit dependence on time. And the simplest Lagrangian density for a real scalar field is half eta mu nu del phi by del x mu, del phi by del x nu, minus half m square phi square. By the way, I will use the convention that h bar, I have chosen my unit system such the value of h bar is 1, the value of c is 1. Okay. Again, flat space time, some Minkowski metric is appearing. Indices are repeating, meaning they are being summed over from 0, 1, 2, 3. Okay. So this is my Lagrangian density. Now I want to do quantization. For quantization, we have to canonical quantization, not path integral quantization. There is another way of quantizing called path integral quantization, where you don't have to go to the Hamiltonian formulation. But we are adopting canonical quantization, so therefore we need to have the Hamiltonian. For Hamiltonian, first of all, I have to have the notion of canonical momentum. There the canonical momentum P was del L by del x dot. Here, instead of x, the degrees of freedom are the phi. So the canonical momentum phi, which is a function of x and t, by definition therefore is derivative of the Lagrangian density with respect to del phi dot. Just like in the case of few degrees of freedom problem, the canonical momentum P is del L by del x dot. Here it will be del Lagrangian density divided by del phi dot. That will be the canonical momentum density. So this is phi dot. Phi dot meaning derivative with respect to time. So let's see what that is. If you expand this, there is nothing but, remember x0 is t, c is 1, x0 is t. This is nothing but phi dot square minus grad phi dot grad phi.
So why Lagrangian is only a function of phi dot, not the spatial derivatives?
Huh?
Lagrangian can also...
No, it is. Sorry, I didn't mention that. Yeah, it is. Okay. I meant not just phi dot, but del mu phi. In this case, it is. Good that you pointed out. Okay. All right. So I have expanded because these mu nu are being summed over. This is your Lagrangian density, and therefore del L by del phi dot you can see is simply phi dot. Okay. Is that clear? And hence my Hamiltonian density, just like in classical mechanics, Hamiltonian density by definition is phi dot the canonical momentum density pi minus L, which is phi dot is pi itself, so this is pi square, right, minus half again pi square okay, and hence I get my Hamiltonian density for the real scalar field half, so everywhere there is a half. So as you can see in this problem, Hamiltonian density is positive definite because it has pi square, it has grad phi dot grad phi, it has plus m square phi square. So Hamiltonian density is positive everywhere. By the way, someone might think that a real scalar field is too idealized, but that's not true. You can use the real scalar field theory for relativistic fluid dynamics. If you had taken complex scalar field, you could have used it for superconductivity in Ginzburg-Landau formulation. So this has applications also. It's not just for educative purpose. Right, so this is my Hamiltonian density. So far good, and we can find out what are the equations of motion, and equations of motion whether you take the Hamiltonian formulation or the Lagrangian formulation. In the Lagrangian formulation, just like in classical mechanics, in the Lagrangian formulation, what are the equations of motion? D by dt of del L by del x dot minus del L by del x is equal to 0. This is the Euler-Lagrange equation of motion in classical dynamics, which is same as Newton's force equation. Okay. Similarly, in relativistic field theory, I am not going to prove it, but it's obvious. All you have to do is do the action. What will you have to do? Action by definition is integral of the Lagrangian, which is same as integral of Lagrangian is, so there's a three-dimensional volume, there's a time volume, so it can be written as Lagrangian density of d4x. d4x is both spacious volume t cube x and dt. And then you say the evolution of the fields are such that action is minimized, the same least action principle, and the equation of motion that you can derive is the Euler-Lagrange equation for a field is given by del mu of del L by del mu, no, del mu of phi minus del L by del phi is equal to 0. Note the formal similarity with the Euler-Lagrangian equation for a mechanical system. Anyone who has not done it ever, just do it. It's very straightforward, very simple. That by demanding that the scalar field evolves in such a way, the real equation of motion minimizes action. That means about the real solution, a tiny variation of action, del A, is 0. You can get the Euler-Lagrange equation of motion for the fields. Okay. And from the symmetries, there is something called Noether theorem. Just like in classical mechanics, if your Lagrange Lagrangian has a cyclic coordinate x, there is a momentum conservation. If there's no time dependence of the Lagrangian, then there's energy conservation. Similarly, if your Lagrangian density doesn't explicitly depend on time and it also explicitly doesn't depend upon space, then you can derive a conserved energy momentum tensor. T mu nu, a conserved energy momentum tensor. I'm not going into that. When you do that, you will find that the energy density T00, the 0 component of the energy momentum tensor, turns out to be the Hamiltonian density that we have obtained. And the momentum density, which is the 0th component, by the way, I will talk about energy momentum tensor in much more detail because it will be important for general relativity. Here I am only giving a snapshot. T0i, the interpretation of T0i, it is the momentum in the ith direction, its density. So, ith direction momentum density, and you can show that for the real scalar field, it turns out to be phi dot times del phi by del x I. I'm not going to show because it takes a lot of time to obtain the energy momentum tensor using the Noether theorem. Okay, so far it's all classical theory, no quantization as such. And if you apply, so take the Lagrangian density which is given, if you just plug in this, you will find that for the real scalar field, the equation of motion is simply the d'Alembert of phi plus m square multiplied by phi is 0. This is the so-called Klein-Gordon equation. It is the Klein-Gordon equation. Okay. Klein-Gordon equation, we know the exact solution of the Klein-Gordon equation. Okay. What is the exact solution? The most general solution of the Klein-Gordon equation is this. I'll first write it down and then you can show that it is the most general solution. Summation of, I can do an integral over all modes, but at the moment I'll deal with summation. Mathematically everything is simpler. Summation over all momentum modes, k, k1, k2, k3. I have discretized it. You know that if you do the problem in a big box and impose boundary condition, then momentum becomes quantized. This we have done it in quantum mechanics. So I am assuming your field, everything is done in a big box with boundary condition, then the momentum get quantized, k1, k2, k3. So the whole thing can be written as summation over k e raised to power minus, remember h bar c I have set to unity, omega kt minus k dot x plus ak star e raised to power I So in flat space-time, this is the exact solution of the Klein-Gordon equation, provided omega k, this omega k is related to k vector. So omega k is simply square root of k dot k, which is k square plus m square. It's very easy. Just apply this box operator on this. You'll find that if omega k is square root of mod k square plus m square, this whole infinite, remember k is being summed over, that means each mode is a solution. For any arbitrary wave vector k, this term is a solution of the Klein-Gordon equation. And because Klein-Gordon equation is a linear differential equation, therefore, if there is a mode k for which this is a solution, for any mode k, it will be a solution, because box plus m square operator is a linear operator. In other words, linear superposition is valid. So I am superposing every mode. Now, coming back to curved space-time, what happens in curved space-time is the box phi plus m square phi will get modified. Box is no longer the D'Alembert del 2 by del t square minus the Laplacian operator, right? So there will be complication. For Schwarzschild metric, we will do the box operator is 1 over root minus g del by del x mu of root minus g alpha beta del by del x alpha. So the metric and the derivative also come in, and the solution, the modes are no longer such just constants ak, and it's those modes which will become important for particle production, because there is no unique way of defining vacuum. In the flat space-time, there is no such problem. There is unique definition of vacuum. Of course, I am preempting. I have not even told you what vacuum is. We'll come to that. Oh, it's already close to 11. Probably we will need one more lecture. It's already close to 11. Yeah. So far, everything is classical theory of a real scalar field. Now we will apply the canonical quantization technique. Remember the canonical quantization technique. In the canonical quantization technique, just like x became Hermitian operator, your phi will become now a operator. So would your canonical momentum field xt will become an operator. And the commutator bracket, now the commutator bracket of these two equal time, I'll use the equal time commutator. So time will be same, but the spatial point will be different. Why? The equal time operator, there is a I h bar, but h bar I have set it to unity. So I, the Dirac delta function, x minus y. Okay. Remember, in pure mechanics, quantum mechanics, x comma p is I h bar. Here it says that is equal time commutated. It says that if x is not same as y, if you're taking the commutator of the scalar field at one point and momentum field at another point, then commutator is 0. But at the same point, it is not. It is del cube x minus y is not defined even. It becomes infinity. You might ask, why is it so? Why is it that the field variable phi and its canonical conjugate momentum at the equal time at two different points, the commutator bracket is 0? Why? Can someone tell me? It's something I have mentioned about the physical significance of.
The localization of the position and its momentum?
No. It is to do with measurability, causality. Very good. See, the point is, I told you that if two observables don't commute with each other, they cannot be measured simultaneously. Agreed? Okay? That we know. We have derived in quantum mechanics the generalized uncertainty principle. Generalized uncertainty principle says that if there are two observables A and B, then delta A into delta B is always greater than or equal to half expectation value of the commutator of A comma B. This is something we prove. So if two observables don't commute, then there'll be uncertainty. That means you can't measure A and B simultaneously with precision. But someone will say that if at the equal time I am trying to measure phi, and phi is the configuration field, and the corresponding canonical momentum, at equal time, if I am looking at two different points, I should be able to measure, because they are beyond each other's causal horizon, and I should be able to measure. This is ensuring, because at equal time, if x is not equal to y, it is 0. I can measure. Is that clear? It is very important. So this is called the microcausality in field theory, that if two observables are not in each other's causal connection, then I should be able to measure them exactly. Okay? So this is ensured by this. Right. So now the canonical quantization, this must be imposed. But you will say that, okay, can we Dirac used the A and A dagger to solve the problem so easily for harmonic oscillator. So we should do the same using this. So now in the canonical quantization process, AK and A star K, they should be elevated to operator. So in other words, we can write our scalar field over all momentum modes, summed over all momentum modes. Now AK has become an operator, AK into e raised to power minus I omega k t minus k dot x plus the complex conjugate of AK has now become dagger, because it is an operator, and therefore it has become its adjoint. Okay. What is the momentum density, canonical conjugate momentum density operator then? Remember, phi operator is simply time derivative of the pi operator is time derivative of phi operator. This I can write it as. Now it is being summed over k, but here if I summed over k, here I'll sum it over k prime. They are dummy momentum modes. And because I am differentiating with respect to time, there will be a minus omega k prime will come out. So minus iota omega k prime will come out. Equal commutated time. Time is same. Y plus I omega k will come out. Prime okay. So in terms of AKs and A dagger Ks, my field phi and the corresponding canonical conjugate momentum takes this. Okay. So the Sanjeet's lecture is at 11:30 and there's a tea break. I'll just take 5 minutes to write down. So put this together, phi is this phi, put them in the commutator bracket. Okay. You will find when you do it, then what are the commutator bracket for AK and AK dagger? Just like X comma P equal to IH bar gave us the commutator, A with A dagger commutator was identity operator. You'll find when you do this, the commutator bracket for A's are this. I'll stop here, then we will. So is 0, so is but AK with AK prime dagger is delta K, K prime. Okay. So the canonical quantization commutator relation, this one, when you substitute all these, results in the commutator bracket for the AKs in the following way. And this you can see reminiscent of the simple harmonic oscillator. AK and A dagger K is 1, but AK with A dagger K prime is 0. Okay. So I'll stop here. I will need perhaps on Monday, probably sometime I can complete the. No, afternoon let TP do the thing.
We have
Some slot. Let's see. Because I would want that people should, whatever has been done, they should, if they have never done it before, they have to let them go through it once, so that because what happens is continuous degrees of freedom. When you talk about continuous degrees of freedom, there are integrals that will lead to Dirac delta function and so on. So remember one thing, although I am writing it as sigma summation, truly speaking, these are integral modes. So this summation you should take it as this. I have written it so that I don't want to carry a baggage. Truly speaking, what you should be using is integral d cube k by 2 pi cube and 2 omega k factor. You should be using this. And then there are this Dirac delta function which will keep on appearing when you integrate, because these are continuous degrees of freedom. So those are the additional mathematical elements that enter because we are dealing with infinite degrees of freedom.
So I have a main question, sir. This m squared, for a real scalar field, this m has to be real, right?
M is real.
But from the symmetry thing, we can say that m can also be complex, and m can have a phase.
Which symmetry?
I mean, unless and until we quantize it and assign this field to be some kind of a particle, m can also be a complex number.
No, wait a minute. We are talking about real scalar field, right?
Yeah.
If you talk about a real scalar field, then the Lagrangian density has to be completely real. So m square better be something positive, or m square better be a real number. So m cannot be an arbitrary complex number. But Lagrangian density under no circumstances should be non-real. Even in the case of Higgs field, you see Higgs field, your mu, so the Higgs field cannot be taken to be a Klein-Gordon field, because the Higgs field is, the mu is imaginary actually. So that mu square comes with opposite sign. But even then, mu square is real.
Similarly, a scalar field can be complex, right? So for
Scalar field can be complex, but the Lagrangian density has to be real. For a complex scalar field, the Lagrangian density will be half eta mu nu for a complex scalar field. Correct? Complex phi. It will be half eta mu nu del mu phi star del nu phi minus half m square phi star phi. What?
M is always a real quantity.
No. So Devabrata's question is, why not take M to be complex? So my answer to his question is, you better not put M to be complex, because Lagrangian density has to be always real.
And M is not a vector from the Hilbert space.
No, M is not. M is a parameter. No, M is a parameter. So Devabrata's question is, after all, I could have taken a complex scalar field where phi is complex. I deal with complex. So his question is, if I can use a complex phi, why can't I choose a thing where m square is complex? But you can't choose m square to be complex, because Lagrangian density has to be real. But you can ask, well, how about using a situation where instead of taking m square, you take mod m square. Take m to be complex so that mod m square is real. That is allowed. But then you will have tachyons. As you know, I mean, I was telling the students that Sudarshan he was a genius, right? Sudarshan had a great brainwave that I talked about this result, that in special relativity, the inertial mass from the moving frame is rest mass divided by this. And I use the fact that because energy is same as mc square, nothing can move faster than speed of light, because if something moved, energy or the inertial mass becomes imaginary. But Sudarshan, being a creative guy, he said, how about particles whose rest mass themselves are imaginary? For that, V can be necessarily greater than C, so that the actual measurable inertial mass is real. So probably Devabrata wants to explore that, how about making m to be complex, and instead of having m square, you have mod m square. That will be a different theory. Try to explore it and see whether you get something new. But the problem is, in the classical theory, you will find your equations will always come with mod m square. So it doesn't matter. You'll never get m, you'll get mod m square. But this for the scalar field. But in the Dirac, if you choose a Dirac field, in Dirac field, the equation of motion comes with m, not m square. Yeah, so these are the things which should be explored. That, can I change this to imaginary? What do I get? So that's what theoretical physicists do. They play games with mathematical objects. Any more questions? Don't use the terms, that is the old term. What people earlier thought that, look, in the canonical quantization, we quantize, we make the operators, we take the classical observables which were non-operators to operators, we get our wave function. But then people said that, okay, phi probably is the wave function. In the earlier days, people thought that the Klein-Gordon phi can be treated as a wave function, and when you quantize, you are quantizing the wave function. And that's why they talked about second quantum. It created a lot of confusion. Today we know that phi cannot be used as a wave function. That you know, even if you read standard quantum mechanics book, they tell you that the Klein-Gordon field phi cannot be talked about as wave function. Why? Because the probability density for a Klein-Gordon field, you can prove, is, even for a complex Klein-Gordon, is phi star del phi by del t minus phi del phi star by del t. And it is not positive definite. It leads to negative probability density if you treat them as wave function. So the word second quantization is only a very old term. I mean, it was there when we were graduate students, when we were learning quantum field theory, and it led to a lot of confusion in us.
So,
Yeah.
when we are able to write this, let's say phi x, phi tx as the combination of AK dagger with the mode solution, let's say UK star, as a plane wave solution,
Yeah.
is I eligible to do this because I am starting from a non-interacting plane? Is that the reason? Or if I take an interaction term, these solutions also will be.
No, but if you have an interacting field, so you have phi interacting with a mu, let's say, then there'll be cross terms, right? So then you have to say that I will quantize phi, I will quantize a, both will have operators and there'll be interaction term. The current, phi current will be coupling with a mu. A mu will be, a mu j mu will be a coupling term. So you have to be careful about, and interacting field theory quantizing is a very non-trivial task.
Sir, as he asked that if the m is complex number, is that the notion of causality still holds true? That phi star and
What?
pi star, and that notion of the causality.
No, causality is only at the level of commutator bracket. This commutator bracket with the Dirac delta function ensures that at the 2 points that are spatially separated, they are in not causal contact, I should be able to measure both momentum and position. And therefore the commutator bracket must be 0. So although I have formulated in equal time, but you can make it more relativistically covariant, you can say it may not be equal time, you can say that microcausality imposition is commutator of phi at event x mu with momentum pi at event y mu is 0 if x mu and y mu are space-like separated. Otherwise, it is the delta 4, the 4-dimensional Dirac delta. You can write the commutator relation in a more covariant fashion. I have not written it in a covariant fashion. I have written it at equal time commutator.
Sir, one question that the canonical commutation relation, that x and p cannot be measured simultaneously and accurately. So
It follows from non-zero commutator. Because there's a theorem you can prove in linear algebra. If two operators don't commute, you can't have simultaneous eigenstates.
yes, but what happens if physically?
Physically, it's consistent with the collapse approach. So, yeah, it's an important question. Why is it that if two operators which don't commute, therefore they can't have simultaneous eigenstate. So why is it that you can't measure simultaneously? Because go back to the postulate, fifth postulate that I wrote down, that when you make a measurement on an observable, it collapses to the eigenstate of that observable. So if you have two observable I'm trying to measure simultaneously, it better collapse to a state which is simultaneous eigenstate of both the observable. Otherwise I can't measure both together, right? That's the reason.
I have read somewhere that if you measure the position of the particle, I have to bombard photons on them, then that disturbs the system.
No, that is a theoretical Heisenberg gamma ray microscope thought experiment. That's the physical way. But mathematically, so that is physically, yes. So in order to, if you take a microscope, gamma ray microscope as Heisenberg used, that how do I localize the particle's position very accurately? Because the diffraction limit of a microscope, the least angle you can measure, the separation between two particles, the least you can measure is diffraction limited. What is that thing? It is lambda divided by 1.22 times dimension of the microscope, d, diameter of the lens. Only when lambda goes to 0, you can reduce your uncertainty in the position. Lambda going to 0 means what? You are using higher and higher frequency. But then Heisenberg noted, if you are using a probe whose lambda is 0, its momentum is very high by the de Broglie relation, because lambda is h by p. If the momentum is very high, it interacts and it transfers an uncontrollable momentum. So you don't know what the momentum is.
I get that, but why it is not a problem for if I measure x and y simultaneously?
It is a
X and
no.
y I can measure, right?
Correct, but with same, you use if you are not bothered about momentum. So go back to your Heisenberg microscope. So this is your lens, this is where you are observing, this is your focal plane. The focal plane is two-dimensional, x and y, okay? And an electron is somewhere and you are radiating with gamma rays. The electron can be here when the gamma ray strikes it and enters the lens. So it doesn't matter. This point, if your lambda goes to 0, this point, both x0 and y0 coordinate, you can accurately measure. Position is not a problem. You can both, the exact point of the plane in the limit lambda tending to 0 can be measured. But lambda tending to 0 means once the photon has struck the particle, its momentum we don't know. It has imparted a huge momentum. If lambda goes to 0, the momentum of the photon h by lambda goes to infinity. That is the physical way. But someone will say, oh, that happens only in a microscope. Maybe there is a device which can beat. The answer is no, because it is all in this mathematical result, x comma p equal to I h bar. Postulates of quantum mechanics ensures whether you take Heisenberg's microscope or you take a board with a narrow slit. Narrow slit is the same thing. I mean, you may say that I will not use Heisenberg microscope. I pass particles within a tiny slit. So you have particles coming in, and I know if the shutter opens for a small time t plus delta t, when the plane waves pass through this, at time if the shutter is open, and if I find the particle here, it must have passed through this tiny point, and therefore I know its position. But if you try to reduce the aperture of the hole, make it more and more, the diffraction is much more. The particle can be going in any direction, the momentum is not known again. So no matter which kind of apparatus you choose, you cannot beat the uncertainty principle. And that is ensured by the commutator of x and p being non-zero. Okay. Yeah, I mean, you have to think about it. I mean, in my undergraduate days, I used to try to think of all possible ways of beating uncertainty principle. I couldn't, but then I slowly realized you can't, because mathematical axioms of quantum mechanics precludes the simultaneous measurement of two operators which do not commute, because you can't have simultaneous eigenstate, and this is consistent with the collapse picture. So collapse of the wave function is consistent with x comma p not 0 and the uncertainty principle.